I have a multiplier design here. Now I know what it's like sometimes when you get these black box descriptions, that you get a kind of understanding but not enough for you to go and build a circuit or understand it properly. So what I'm going to do is take our time and we're going to work our way through the description of this in detail so we can get a good understanding of how it's working. Now we'll also at the end compare this to the VBA multiplication which we've seen in our VBA tool. So let's get started on this. We start up at the top and we've got our input X and we've got our input Y. Now the input X is the 32-bit single precision floating point binary number, and the same for the Y. And we've got our output at the bottom, which is going to be our X times our Y. Now the first level here, we've got a couple of boxes. Now those boxes are used in order to split the signal for our X and our Y into the sine, the 8-bit exponent and the 23-bit Mantissa for both X and Y. Now an overview of the circuit, we have three different sections. We're interested in operating on the sine bit and we do that here. We're interested in operating on the exponent bit, so the addition of the exponent is done here. And we're also interested in the multiplication of the Mantissa and the rounding, and that's done in this section here. So let's talk through each of these sections individually. Now the simplest one is going to be our sine bit. We said that in order to generate our final sine output, which we've got here, so I've called it large S and O for output, so this is the sine of the output. We're going to have to take the sine of X and the sine of Y, and we have to exclusive OR them. Now when we've exclusive ORed them, the final output will be our sine here for the output. So that's relatively straightforward. So let's now go on and we'll look at the exponent. Now we know we want to add the exponents, so we take the copy of our exponent. Now this is our biased exponent, so the actual exponent that exists on our 32-bit input is a biased exponent for X, and we've also got a biased exponent for Y. Now I haven't drawn it out here, but when we go to this point, we're actually subtracting off our 127 in order to get our small ex, which is our unbiased exponent. And the same for this part here, we subtract off our 127 from our large sy, ey, and we get our small ey. So these here are our unbiased exponents ex and ey. Now we know that we have to add those together, so we put them into a summer. So at this point here at the output, we take a copy which of ex plus ey goes this way, and a copy of our ex plus ey goes this way. Now we're going to put them into a couple of summers. Now the reason why we're going to do that is because if you remember the algorithm for our normal times a normal giving a normal output, we said that the output for the exponent is going to be our ex plus our ey plus our bias plus the value of 1 or 0. Now the 1 or 0 is determined by the 48th bit of the multiplication. So here's the multiplication here, and we're taking the 48th bit of this multiplication, so let's take it down here. Now ignoring this OR gate for the moment, this 48th bit comes in and we use this as a choice. So this 48 bit chooses whether we add a 1 or we add the 0. And we've got the multiplexer here and we choose adding a 1 or adding 0. So what we are doing here with this plus this adder here and this adder here is we're making a copy of the two possible outputs, ex plus ey plus b plus 1, which is here, and just ex plus ey plus b, which is this one here. So we've added the plus b on in here, and we've added the plus b, the b plus 1 on in this one. So when we come down here, we choose whether we want the output to be the +1 or just the +0, and the choice is made from the 48-bit of the multiplier. So the final output here is E out, so I've just got small e out, so that's going to be our EX plus EY plus the value of 1 or 0 and plus the value of B. So this E out plus B is in effect the final biased exponent, which I've written down here as big E naught, so it's big the 8-bit output that we're looking for. So that's us covered the sign and we've covered the exponent. So let's now go ahead and we'll cover the mantissa. Now you can see here that we have the mantissa for X, which is the 23 bits coming in here. We'll get a mantissa for Y, which are the 23 bits coming in here. Now between this point here and big MX, you'll see at this point I've called it 1 dot small mx, and I've called this bit 1 dot small my, because between this point here and this point here we've actually appended the 23-bit mantissa with an extra bit. So this 1 is the 24th bit or the hidden bit. So now we've got a 24-bit value for Y and a 24-bit value for X. We're going to multiply these together and we're going to get a 48-bit output. So we've seen in the previous video when we worked out our algorithm for a normal times normal giving a normal result that the mantissa will shift by a value of 1 to the left or a value of 0. So by shifting, what I mean is the decimal point can shift one place to the left or it can remain where it is, and that shift is dependent on the value of the 48th bit of the multiplication. And you can see that I've drawn that in here. We've got the 48th bit of the multiplication in here, and you can see it comes down and it goes, we've got one copy goes into the exponent, which we've talked about already, but there's another copy goes into this multiplexer here, and it'll choose either one of these, this value here, or it'll choose this value here. Now this is the thing about black box representation, you don't get the complete picture, so let me try and explain this here. Between this point here, which is the 48 bits, the copy here we get down here and into this point here is different from the copy we've taken from here. So what we've done is we've taken the 23 bits of the mantissa in here and a 23 bits of the mantissa, but the mantissa is going to be started from a different position at this side here from this side here. So if you like, there's a little bit of circuitry in here which is not shown, but which we will build whenever we do actually build up our floating point unit in the next course, which will shift the mantissa to the correct position. And we'll take a copy of that mantissa in here and a copy of the unshifted mantissa here, and we'll choose between the two. And that choice will be made by the 48th bit. So again, we're going to have a look at this before the end of the video in the VBA example. They're using our multiplication tool, and we'll talk through it with respect to that, and it'll become quite clear what we're doing here. So that output then is this point here is the actual 23-bit output of the mantissa, and it's starting at the right point, so either starting at the original decimal point or the decimal point one place to the left. So let's have a look at the rounding section here. Now the output we get here from this mux is the 23 bits. Now the 24th bit, that's the one after that, is going to be a guard bit, and we've got the guard bit represented here. Now we're also interested actually in the 23rd bit for this as well, so we'll have the 23rd bit for this also heading into here, although I haven't shown the line here, there should be a line here. for the 24th bit heading in here. Now we're also interested in the other 22 bits that sit to the right of the guard bit, and those 22 bits are the bits that get ORed together to produce our sticky bit. Now each of these go into the rounding section along with the 48th bit here, which we're not using for the moment but does get used in the rounding section for certain modes. So these are all the inputs that we need into the rounding section. Now I'm not going to go over the rounding again. You can also have a look in the video on rounding, and you can have a look and see how this is working. But ultimately what's going to happen here is we're going to get an output here which is either going to be a 1 or a 0. So it's going to tell us that we need to increment the 23 bits here of the Mantissa. So we'd have to add a value of 1 on to the least significant bit of the Mantissa, and that value of 1 will potentially ripple all the way up through the Mantissa. And you can see here we've also got an output here, because that value of 1 could ripple all the way up through the Mantissa and then into the exponent. And this is why we have this extra section here. So this is another input to this OR gate, and this could increment the exponent by a value of 1 as well. Now a thing to note here is that the exponent will only ever be incremented once. It will either be incremented through the 48th bit here going high, or it will get incremented through the rounding bit here going high and rippling through up into the exponent. It won't increment twice. So finally what we can do is we can take the exclusive OR of the signs, which is our big S0, we can take our exponent here, and we can take our Mantissa, and then we can add them all together again, or we can concatenate them into one single value, and this is going to be our output x times y. So let's go ahead and we'll have a look at this in the Excel tool that we've built, because the Excel tool just models what we have here in the software. So that's me ran up the tool. We'll put in a couple of numbers. Let's say we put in 50 times 100. And you can see here when we do 50 times 100, the 48th bit is a value of 1. So we know we're going to have to normalise the result. So we're going to shift this decimal point from here 1 point to the left. But first of all, we'll have a look at the exponent. We can see here that we're going to have the 50 is going to have this exponent here, and that exponent is 132. We take away the 127, we get a value of 6, and the same for the y section. We take the 133 here, we take away the 127, and we get a value for 5. So let's have a look at that in our diagram. So if I can bring up the page here. Okay, so that's us here. We've taken the value of our EX, taken away the 127, and we've got our value here for small EX, and we've done the same for EY. We've taken away the value 127 from this big EY, and we've got our small EY, and now we're going to add the both of them together. So let's go ahead, we'll get this little bit and this little bit here done. So we'll head back into the spreadsheet that we're interested in. So we then go ahead and we add both of them together. We get our value of 11. Now we're going to either add 1 or not add 1 to it. Okay, so this is the two options that we have, and we create a copy of this xe plus ye, and option 1 is that we don't add any bias, so we'll have an xe plus ye plus the bias. This is this answer here, xe plus ye plus the bias, and we'll either have the plus 1 or we'll have the plus 0. So again, let's have a look back in here and we'll see it in our drawing. If I can bring it up here, there we go. So we're going to have our addition ex plus ey, and we're going to have the ex plus ey plus the b, and we'll have another copy of it, ex plus ey plus the b plus 1. And then we have to make a choice between these two, and the choice we make between these two is going to come from the 48th bit of the multiplication. So let's look at the 48th bit of the multiplication there. Okay, so we've got the 48th bit of the multiplication as a value of 1. So whenever it's a value of 1, we know we're going to have to choose the ex plus ey plus b plus 1. Okay, so that's going to give us our correct output for our exponent. So that's relatively straightforward. So let's have a wee look at the Mantissa. Now in this instance here we can see the right answer. The right answer here is going to be 0, 0, 1, 1, 1. Okay, so and that is seen here because what we're going to have is we're going to have the decimal points move from here to here. So we're going to have our 0, 0, 1, 1, 1, and this will give us the correct output. So what we're going to do here in this instance is we're going to make a choice of 23 bits. So the 23 bits we choose is either going to start from this point here, so it's going to be 0, 0, 1, 1, 1, 0, 0, and so on, if we have to shift a bit. So that's one option. The other option is that we don't shift a bit and it starts from here, and we have an output which is 0, 1, 1, 1, 0, 0, 0. So we've got two different options again that we can choose from. We can choose from the one where the bit has been shifted, and we can choose the one where the bit isn't shifted. So let's have a wee look and we'll see that in our diagram here. So again, this is this point here. We can see here that we've got an output here, and we're actually at this point, although we haven't shown it here, we're making a choice between two possible 23-bit combinations. One of them is shifted by a value of 1 and the other one isn't shifted by the value of 1, and we make a choice again of the two that we're going to choose depending on the leading 0. So if it's a 1 at the 48th bit, we know we're going to choose the left shift plus 1, and we know if the 48th bit is a 0, we're not going to left shift, so the left shift in effect will become a 0, and this is the output we're getting here. So let's go back in and we'll finish this off. Okay, so now we're able to make the correct choice. Once we've made that correct choice, we're interested in looking at the rounding. So what's going to happen is we're going to go from either this point here, or the start of the 23 bits will either be this point here or this point here. So we'll be counting 23 bits from here all the way along. Okay, so this is going to go from you see I've noted down at the bottom here, I've called that O0, so that's output 0. So it's going to go from output 0 and it's going to go along to 23 bits. Or it could start from this point here, output 1, and again go along 23 bits. But what matters is that the next bit after the 23rd bit is going to be the guard bit. And of course we're interested in the guard bit, and we're interested in the other 22 bits which are beyond the guard bit. So in this instance here, it's going to be from the position here, output 25, which is this point here, and we're going to have the 22 bits afterwards. And those 22 bits are going to be ORed together in order to give us our sticky bit. So in the end, for our rounding, we're going to end up with the 23rd bit of the output here for our multiplication. So this is the 23rd bit here, and we're also going to end up with the guard bit, which is going to be the next bit, and we're also going to end up with the next 22 bits ORed together, which is going to be our sticky bit. And those are always going to get into our rounding block, and we choose what rounding method we want, and we'll either get a 1 rippling up through the significant and potentially the exponent, or we'll just get a 0 and nothing will happen. So finally we're going to have to concatenate, that is join together the sine, the exponent and the mantissa to get us our final value. And you can see here that we take the exclusive OR of the two sine bits here, and this gives us a sine of our output. We take the exponent value here, which we've calculated, and this is our exponent value here. And finally we take the mantissa value, and you can see the mantissa value here. In this instance the highest bit's a 1, so we've had to shift the decimal point, so we've had to normalise it, so the actual mantissa is going to be go from 0, 0, 1, 1, 1, and you can see we've got a 0, 0, 1, 1, 1 here, and this is the rest of the bits. And finally we're going to have a copy of this 32nd bit, and we're going to have our guard bit, and we're going to have the OR of the next 22 bits after the guard bit, which is going to be our sticky bit. And this can ripple all the way up through and potentially ripple up through into the exponent. And we'll finish off just looking at the diagram we've drawn, because that's us pretty much finished everything we need to look at. So that's us joined the sine, the exponent and the mantissa together, and we've got our final output, which is x times y. So in the next course, whenever we actually do the floating point unit, that is, we're actually going to build one or realise one, we will be using this basic architecture, but we'll be extending on it. And of course we still have to extend on this with the possibility of receiving subnormal inputs. So we're going to look at that next. Thank you for listening. I'll get you on the next video. Goodbye.